So I think I can hear a bit of echo. So maybe perhaps people could please mute their microphones. So welcome to the next Impact Research Seminar. Our speaker today is Dr. Ashkan Pakzad, who joined Project One of Impact almost a year ago. Before that, Ashkan was at the University College of London, where he got his Master of Science in Medical Physics, and then a PhD in medical imaging, specializing largely in application of AI to image analysis and segmentation. So today he will present a talk, his initial results on AI denoising of breast phase contrast images collected by our team at IMBL. Okay, Ashkan?
Thank you. I'll start by sharing my screen. Can you see my screen? The slide?
Yep, works well.
Great, thank you. Now I've included a fair bit of background information, which looking at the attendance list might not have been as necessary. Yeah, please bear with me. So I'll begin. Yes, so I'm Ashkan. For those of you that don't know me, I'm in the School of Physics at University of Melbourne, and I have strong interest in medical image processing and analysis, and I'm supervised by Harry Quiney and Tim Graev. So today we'll be talking about taking phase contrast breast CT further with AI denoising. So breast cancer, even across both male and female populations, has been shown to be the most frequent. And early detection is required to avoid fatal outcome. The two main stays of breast imaging, breast screening, is 2D X-ray mammography and breast tomosynthesis, where we have on the left the mammography showing how a single projection is 2D X-ray projection is essentially taken. And on the right, we have the pseudo 3D breast tomosynthesis, showing how we can take apart layers in the imaged breast. And so in tomosynthesis, this is done by capturing multiple X-rays through a limited angle. And breast tissue can largely be categorized down to glandular tissue, which appears bright, and adipose, which appears dark. And here, just this arrow is pointing out a suspicious mass and how moving towards 3D imaging can help be able to identify these masses better. So radiologists are looking for bright structures amongst bright structures. And the breasts can vary in what is called radiodensity. Essentially, this ratio between the glandular and the adipose tissue, where a more radiodense breast can often produce greater challenges in visualizing these masses. So we want to achieve the best contrast between the tissues, and we want to reduce noise as much as possible. So in our studies, all imaging is conducted at the medical beamline, the imaging and medical beamline, IMBL, at the Australian synchrotron, where we're imaging as close as possible to real patients. So we're using clinically required mastectomies with patient consent, and the mastectomies are transported immediately to the synchrotron and are scanned without fixation. And this is part of an ongoing project. And specifically in this study, we have been imaging 34 breast samples, and where 6 of them have been held out for testing, and the remaining have been split into 5-fold cross-validation. So in X-ray CT, we are looking at a true 3D volume, unlike, for example, tomosynthesis, which I showed earlier. We have an isotropic spatial resolution, and we're imaging the breast without compression. So this is in CTs achieved by taking these 2D X-ray projections at multiple angles through 180 degrees rotation or 360, and we reconstruct the slices into a 3D volume. Now, the main source of noise in these images is due to Poissonian noise. So the signal variance is directly related to the number of photons, as is in photography. If you ever try to take a picture in low light, and increasing the number of photons reduces the noise. And then the technology that we're imaging here is known as phase contrast inline. So typically in absorption-based imaging, let's say, more conventional imaging, we place the detector right behind the object of interest and measure photons that are recorded on the detector, and we form an image based on the X-ray absorption of that object. Now, at the synchrotron, when we have coherent X-rays at a single frequency, we can push the detector out and we can record these changes. We can record the phase of the X-rays as well, so that the shift of the X-rays due to refraction as well as absorption. So we now have an image based on the contrast of absorption and refraction of the object. And we can do what's called phase retrieval. So we can retrieve that phase, and we can use that information to reduce the noise, already. And that's using despite using the same number of photons. So X-rays are ionizing, and the higher the X-ray dose, the greater the risk of inducing cancer. Typically in breast.
Can I just
Oh, sorry, I didn't realize there was a hand up.
Yes, Keith? Keith? You wanted to ask something? You are muted, Keith. You are muted.
Is that okay? I'll go ahead for now. That's okay. So the dose is typically measured based on the dose absorbed by the glandular tissue, the bright white tissue, which is known as so we're interested in the average dose to that glandular tissue, the mean glandular dose, MGD, is typically denoted. And the glandular tissue is highly radiosensitive, which is why we're so interested in the dose that it absorbs. And of course, we want to reduce the dose as much as possible because we don't want to induce future cancers from occurring. However, of course, reducing this dose, as I mentioned earlier with Poissonian noise, results in this noisy, noisy appearance, this grainy appearance. And so if we compare these two images, where we have a lower MGD of what is known as 4 milligray compared to this image on the right at 24 milligray, we can, for example, compare these thin white lines of the glandular tissue, and we can see that the noise starts to obscure them. It makes it difficult to see, which is why we're interested in denoising. So current standards in breast screening, breast imaging, are to limit the, so as I was saying, to limit the dose as low as possible. And the theoretical limits imposed in the US and Europe is 6 and 5 milligray respectively for a single screening, for a screening for what is known as the standard breast. So here the medians are, the range of the medians are reported for the most recent studies in dose delivery. So in digital mammography, we go down to as low as 2.2, in digital breast tomosynthesis as low as 3.2, and the latest BCT scanners as low as 5.1 milligray. And there are 2 dedicated breast CT scanners on the market, which the second generations have recently been released. One is by a company known as Koning, which appears to be is approved in both Europe and the US. And we also have Advanced Breast CT, ABCT, which is available in Europe and approved in Europe. And BCT has been an emerging technology for quite a long time, and that's because it's been this struggle to reduce the dose within this acceptable, these theoretical upper limits of 6 and 5 milligray. And sorry, and so it's made it infeasible. Now, despite these latest iterations being able to produce images at much lower doses, and they are still somewhat higher than digital mammography and digital breast tomosynthesis. However, I just wanted to point out a few characteristics of interest that I think particularly that would be of interest for our teams. For example, both of them are in cone beam geometry, and they take 10 seconds to complete a scan. Where Koning uses a Zinnius-like detector, so that's the detector that is used in the images that we acquire here, and the ABCT scanner, which is known as MuView, is a photon counting detector and appears to have characteristics very similar to the Eiger detector, which we intend to take images with soon. And I just have a couple of example images so you can see what sort of images they capture. And their voxel sizes are around 300 microns, but can be smaller using different scanning parameters. In comparison to the images here, where we will look at voxel sizes of 100 microns, so 3 times smaller. So in CT, we can reduce the dose in 2 ways. We can either vary the number of X-ray projections, the number of views we acquire, or we can vary, so we can vary the number of X-rays per projection, or we can vary the number of projections. So for example, where we have here on the left a reduction in the number of photons on per projection. On the right, we have the same number of projections, but with higher number of photons per projection. And so we could, in theory, well, we can reduce the projections by taking 1/6, and we can get a 4 milligray image. So here in this study, we capture these 24 milligray images and these 4 milligray images using 4,800 projections for both. And using 1/6 of those, we can produce an image that corresponds exactly to the 24 milligray at 4 milligray dose. This study was carried out in collaboration with Robin Simon from the Melbourne data analytics platform known as MDAP.
Can you hear me now?
Yes.
So I couldn't unmute last time. I don't know, and I've gone out and come in now. We're working, so sorry about that. The question I had about the paper in the previous slide, you have a significant number of reduction in number of projections to emulate a lower dose.
Yeah.
Now those two are obviously not quite equivalent. How big an effect do you think that actually is on the image formation? I mean, in other words, you still think when you reduce the number of projections by a factor of 6, there's still plenty of sampling to do as good an image if the photon numbers are the same?
I think so. Yes, sorry. I appreciate they're not exactly the same because you have a reduced sampling. But yes, with 4,800 projections, I think the sampling is still high enough. It still satisfies like Nyquist theorems, for example. And later, I will also be going into similar studies where they conduct something similar and they use far fewer projections. And then I think you'll be more shocked into how far down people go. And also, for example, looking at the Koenig scanner, which I mentioned here, they go down to as low as 300 projections for each of their scans, and that appears to be fixed. Every scan appears to be 300 projections. Yeah, so as I was coming to here, I just wanted to cover denoising in CT. You can come at it from many different angles, and you can look, so you can, and of course, for each of those angles, you can apply deep learning to any of them. So we can denoise projections directly before the reconstruction. So you'd be looking at the acquired signal, and you'd be able to prevent the noise propagation to the reconstruction. However, you need to ensure that you preserve the spatial correlations to prevent artifacts arriving in that reconstructed image. And you could look at iterative reconstruction, so that while performing your reconstruction, you can account for this variation due to noise in your signal. And it was seen before deep learning, it was what appeared to be the most typical approach, however, was associated with being slow. And you can denoise in your final reconstructed images, which is ultimately the domain of interest in CT, where the data is more compact. So you don't need to deal with huge sizes of data in your deep learning process, and you don't need to worry about the projections to implement. And it can, so if you already have so in terms of rolling out, you can apply it straight away, and it tends to be able to be more modular, to be able to slot into existing frameworks. And this is the domain that has typically been targeted in most deep learning research for denoising. So that's where we went ahead in. Excuse me. So looking at research and approaches in deep learning using convolutional neural networks, which have demonstrated to be the best performance over previous methods, there are a number of popular approaches. So there are, for example, I know was also mentioned in the previous impact seminar, looking at noise to noise and noise to self. So these methods don't require a clean reference. So don't require a clean reference clean reference image. It can be applied in either the projection or the reconstruction domain. There is the noise to inverse framework, which also can be used with noisy images. So but using subsets of projections in the reconstruction domain. And then finally, sort of the most typical approach in deep learning, is looking at supervised deep learning, where using a clean or a less noisy image as reference, we can train to denoise noisy images. And this final one is easier to apply. It's easier to apply in the reconstruction domain just by reducing the number of projections as we have, and perform typically the best compared to, for example, unsupervised, where you don't have a reference for a higher dose. So I appreciate Poisson noise is not additive. However, we can still go ahead in this approach of modeling the noise, where we take, say, the image we capture, so this 4 milligray image here, which we denote as Y, and we can consider the less noisy images are sort of our ground truth, our underlying true object, and we can think of that, the difference between them, as the noise. And when we take that model to what we're working with, in which we want to train a model which can denoise our Y to produce our X's, because we've divided our 24 milligray by 6, we have 6 different sets of 4 milligray images. And so we have 6 different independent measurements of noise between which are completely uncorrelated. And we can train the model on to get back, in a way, to that 24 milligray image. So we have our framework, our supervised learning framework, and next we want to focus on the shape of our model, the architecture, and the objective, the loss on what we want to train it on. And we are very interested in perceptible improvement, let's say. Typically, of course, the approach is to go through picking a couple of metrics and trying to make them go up, but you might just get 0.01 improvement. We're looking here for also what we can see with our eyes and tangible, as we're interested based on the feedback that we get from radiologists and radiographers, because we are interested in improvement, what they have to say, and the improvement that they judge. So UNet has demonstrated to have great performance in medical imaging in all sorts of tasks. So that was one of our first ports of call. And we were also interested in attention mechanisms. Here was a model known as ADNET, as they also promise to do well. However, we just, for example, look at the results we get from those. We found that UNet demonstrated best. And so the next task was to see if making it bigger and deeper or smaller by trying different kernel sizes. So that's how much of the image it sees at once, bigger and less. We explored going from the standard UNet, which is here on the far left, to smaller and smaller units, as well as a big unit. It turned out this one in the middle performed the best for us. And lastly, before committing fully to L1, the more basic loss functions of just looking at the differences, which just examines the differences. We're also interested in exploring losses further. And so we considered, for example, deep perceptual losses. So this is an advanced metric that uses another deep learning model to judge how different two images are. But we found that could produce quite a lot of artifacts. And so we went ahead with our slightly smaller unit to examine further. So to evaluate our images, we're interested in this biomedical image quality metric. So what we were particularly interested in, how does dose in biomedical imaging affect quality? So we can take what is meant to be a flat homogeneous patch in the image. So here that's highlighted in yellow, and we can measure the mean and the standard deviation of it, and we can get the signal to noise ratio, the SNR. And increasing the number of photons, which is directly related to the dose, improves the signal to noise ratio squared. So we know this is one way that we can evaluate how the image quality compares to the dose. So if we smoothen that image, we're effectively denoising it, right? But there is, of course, another important element in all of this, which is the spatial resolution, which we've lost. And so in 3D imaging, we know that that is proportional to the dose by the resolution to the cube 1 over. Sorry. And so this gives us our basis for evaluating the biomedical image quality, a reference-less metric, and can tell us the image quality in terms of radiation dose. And the converse of that, this is the toy example. So I'm not necessarily saying we gain resolution, but as a toy example, if we were just looking at sharpening this image, we reduce the SNR and we improve the resolution, supposedly. So the point to make is these 3 images are equivalent in dose. The dose hasn't changed, and it hasn't changed for this measure, which we consider as the SNR squared over the resolution cubed. So if we look at some visual results on a test image, where we go from the far left, which is our input image, to the model, the middle, which was our reference, and the far right, which is our denoised 4 milligray image. Looking at the visual results, we can see how we can start to resolve these small structures, which, for example, these white stroma lines are starting to become visually discernible, and that's telling us that with this visual reduction in noise, we're also not losing the resolution, which is the real challenge, as we can see from before. And radiologists are looking for the morphology in that and the shapes that we can see. And so we can go ahead with an objective evaluation of all this in terms of SNR. So we can measure the SNR in these test images, as I said before. So we have our 6 test images, and I've also included in this graph the smooth images, and we can see how the SNR has increased for denoising, and indeed what we'd expect is that a higher dose would also have a higher SNR. And so our denoising has improved, as it appears, even beyond that 24 milligray reference. However, for that smooth image, as I was saying earlier, once we start to account for the resolution, sort of resolution, it's equivalent for the smooth image. And what we see in terms of our denoising, even when we account for the resolution, it has indeed increased. And we can think of this y-axis from earlier as being equivalent to the square root of dose, which if we look at, for example, a 24 milligram image, which does about 2.4 times better than the 4 milligram, sorry, has a higher SNR over resolution, the power 3 over 2. But to the square, so it's an improvement of the square root of 6, which is what we'd expect between the 4 and the 24 milligram. However, when we look at our denoised images, it's equivalent to a 6 times increase, which corresponds to a 16 times dose reduction. And this is the real result that sticks out from this denoising project. And then if we were to also consider the objective contrast, where we can measure the contrasting interface of two tissues, the difference between the average high to the average low, essentially across that boundary. Interestingly, we find the 4 milligray has a higher contrast, and that's because there's an influence of noise there on the subjective measure of what I just described. And however, it's that contribution by noise is smaller when you compare it to the noise overall, when we look at the CNR that is in this right graph, where we can see indeed our denoised images are higher in terms of CNR. So this on the left is an interesting result, which I like to hold on to for later. I will come back to. So there are two similar studies that use that Koning BCT, and they also similarly went through a supervised denoising. So the Koning BCT acquires images of 300 projections, and then in these studies, they considered producing a low-dose image using 100 projections or 75. So this first rows are from 100, so 12.6 milligrams. So these two on the left are 300 projections, and in the middle two are from 100 at the top and 75 at the bottom, and then denoising them to the right. And so already just from reducing those number of projections, I think you can start to see a loss of resolution, particularly towards the outer edge of the coronal slice. However, if we use a voxel size, if we just were to, for example, consider the voxel size as a nominal measure for spatial resolution, because we don't know the spatial resolution of these devices, when we compare, for example, 273 to our 100 microns, we can consider how that corresponds to effectively a 20-fold dose reduction in our case in comparison. Now, a quick note on calcifications. So calcifications can appear in these images, and they can occur in blood vessels, and they're indicative of cancer presence. So they need to be preserved in denoising, particularly their shape. However, I just want to show you an example of a calcification here from those two different doses. And looking at the histogram, this should say calcifications. That's why I was just curious what's going on there. We can see how they're absorbed, how the calcification's absorption is just so high compared to the rest of the breast tissue that it's not really a noise problem, but more of a resolution problem. And so the solution here is just to threshold those calcifications and let your denoised images inherit it. So following our objective study, we were also interested in a subjective assessment. So this was facilitated by Thomas and Amir at Sydney. So there was 11 assessors, 4 radiologists, and 7 radiographers and clinical medical imaging scientists. And they considered 6 different criteria to assess these images by. And they were blinded to which was the original low dose and what was the denoised image. And they were asked to give it a rating for each of these categories. So just to briefly cover these, we have the, just gonna, so we look at the results of that subjective analysis. We have a few measures here I'd like to quickly describe. So we have this ICC, which is a measure of agreement, where a very high score up to 1 means there's a good agreement. So that's what we have for noise level, and overall image quality. And for calcification visibility and artifacts, we have a high and a fair agreement. Now, there are some negative values in here which indicate a systematic disagreement between assessors as well. And if we look at how these images, how these compare, looking at the score of the AUC for the visual grading curve, where a 0.5 indicates that these images were rated as equivalent. And if it was greater than 0.5, the test image was considered better. And if it was less than 0.5, the reference image was considered better. And the statistically significant results are in bold. So the denoised images were considered overall better than the original and less noisy than 24 milligray. And in terms of the denoised, so the denoised image and the denoised images were considered equivalent to the 24 milligray for all other criteria with no statistically significant differences. So another positive result for the denoising. And the interesting result here is in terms of perceptible contrast, where there was a high level of disagreement. And so there could be possible that it's linked to the objective measures that we were describing earlier, where we saw 4 milligray as having a higher contrast. So following that, we also have been looking at segmentation in these images and its potential as a tool for evaluation. So this is being carried out as a master's project by Amrita at the University of Canterbury with Constantine and Tim, where we're looking at a segmentation of glandular and adipose tissues, which can have applications in looking at dosimetry and evaluating the radio density, where here we have a manual reference. This is where Amrita has painstakingly gone through the slice and labeled all the glandular tissue. And we can use these images, these manual segmentations, to train an NN unit, which is a widely used framework for that self-configuring for supervised segmentation. And so just as a comparison, 2 models were trained, one using the denoised data and another using the non-denoised data. And so as a tool for evaluation, we can see how the model trained on denoised data manages to achieve better segmentation, essentially, where we have many more glandular strands being included in the segmentation. So these are some preliminary results from that project. Next, just want to briefly cover some breast density work that we've been looking at. And when I say breast density, I mean both in terms of physical density and this radio density, this glandularity. So We're using monochromatic X-rays. We have a high isotropic resolution. It's a free 3D modality. So we can get some rich information out of this. And so with a few valid assumptions, we can derive the physical density. So over on the left, we can produce the image mass and compare it with the mass from the pathology labs for each sample. And on the right, we can look at how that physical density, the average physical density across the breast, compares to the radio density. So that is to say, we have a rich amount of information here. And in summary, the dose must be as low as possible, and it always comes back to this. And it's at the forefront in our study compared to what a lot of denoising studies might consider. And what I mean by that is we have been objectively measuring how well our denoising works in terms of dose and dose equivalence. And we're also very much interested in in the subjective viewpoint, of course, of our radiologists and what they think in terms of image quality. So we already have a large dose reduction by phase contrast imaging, and deep denoising takes that as a at least 16 times fold further dose reduction. And this has all been in preparation, of course, for most people know here, is in preparation for live patient imaging in the IMPACT program, where we've used fresh mastectomies, which are as close as possible to live patients. So we're keen to transfer this model to live patient scanning. And if you're eager to learn more, the study's also been released as a preprint, which I can drop the link into the chat later. So coming up was future work. I'm carrying on working with Rob and Simon over from MDAP, where we'll be looking at some diffusion denoising using what has been termed by Rob as dose fusion. We have some large phantoms, which will be made by Alette Engels and has been scanned over IMBL, which we're looking to publicly release with some in one of our studies. And we can also be keen to see what about denoising at lower doses? How low can we go? And of course, with the images coming in with the new photon counting detector, where there'll be an even further dose reduction, be very interested to see what we can achieve there. And of course, many people are involved in this work. And so I want to say thank you so much to colleagues across IMPACT and beyond. Okay. Just one moment.
Thank you, Ashkan. Thank you very much.
No problem. I've got a few slides on.
Ashkan, I think we need some time for questions.
Okay.
Unless there is something which you think is super important,
no, that's good.
Maybe we can let people to ask questions. I'm sure that there are some questions from the audience. Thank you. Okay, so we're open for questions. No more questions? Well, let me ask one, Ashkan. I understand that in principle, I shouldn't be wasting everybody's time here because I could ask you earlier, but since I haven't, one thing which you mentioned during your talk attracted my attention is you said that the noise between the subsets of projections that you select from the, say, 24 milligray scan, when you select every 6 projection and create 6 data set this way, you said that the noise is completely uncorrelated. And I somehow not 100% sure that is true, because exactly the Poisson noise is not additive. So whenever we have a high intensity, the noise will be higher, etc. And whenever it's lower, it will be lower. And it will be true regardless of the instance of the noise, so which in my mind can lead to some correlation. What do you think?
Well, I still think these are all entirely separately captured images.
Oh yeah,
The
yeah, that's
projections are
true.
separately
That's
captured,
true.
and that's where I say that they're uncorrelated.
Oh, I'm just approaching it from the formal point of view. If your method relies formally in some way, mathematically, on the fact that the noise must be uncorrelated, which is a pretty typical and strong assumption, then in this case, what I'm suggesting, it may actually be violated. Right? Well, I guess this is something for the future consideration.
Yeah.
All right.
Yeah, it's something to think about.
All right. Marcus, please go ahead.
Thanks, Ashkan, for an excellent talk. Just curious about one thing, like how do you actually measure the resolution in all of your data?
So in XLI, which is a delightful tool, being built by Tim and colleagues, looking at, so similar to here, sorry, if we go over to here, looking at a flat homogeneous patch as large as possible, and extracting and looking at the power spectrum within that patch.
Okay. Yep.
So, yeah.
Very good. And if I may, I was just really interested in your comparisons with the other scanners that are on the market as well. Do they actually release any data that you can do the quantitative analysis on as well?
No, I've not seen any publicly released data of any sort. No, but yeah, I'd be very interested and very curious.
Yeah, it's just like it sounds like your denoise data is probably a lot better, but just wondering how much the phase retrieve data at the synchrotron is better than their absorption contrast data as well. It's hard to know.
Yeah, definitely be increased because all I can talk about is in terms of these proportionalities.
Yeah, you'd think they should have a public repository at some point, but thank you. Excellent stuff.
Thank you.
Okay, any other questions?
Just a quick question. Ashkan, if you could
Amir, we don't hear you very well. Can you make it louder, please? Not really, no.
My microphone got problem
Oh,
here.
now it's well. Now it's good.
Okay, yeah. I just removed this. If you can go to page 10, if I'm not mistaken, in page 10, you mentioned that
Yeah.
Yes, here we can go for Conning system. Conning system uses 300 projections which seems relatively low. And later you show that they go down by 100 or 70 even. So do you have any insight into what the lowest number of the projection could be while still maintaining sufficient quality for the reconstruction for segmentation purposes?
Segmentation purposes.
Yeah.
I suppose it'd be on what resolution you want in your segmentation. And I would also say, I imagine the people sitting around you are more qualified to say how many projections you can take. By that, I'm referring to the colleagues at IMBL. I don't know exactly. I just know the same rule of thumb for using the Nyquist theorem, which has to do with how wide and the size of your sample and your voxel size and such. So yeah, not exactly, but yeah, as I say, a rule of thumb number, looking at 175 sounds incredibly small.
Marcus, you have another question?
He answered this one in your talk, but just wondering about the projection number again. How do you think that your denoising works for different projection numbers? Do you think it works better for more projections or fewer?
So I suppose if we were to capture, I'm not sure I follow exactly.
Like if you had the same dose, but more or less projections, like more dose in fewer projections, or less dose per frame but more projections, would it handle it better? I guess because with fewer projections you probably get more streak artifacts, which is a different kind of noise. So would it handle the random noise better or structural noise?
So I would say in training, it probably sees images with those streak art. If you were to go very low, you would see those streak artifacts. And then in evaluation, I think it's always best to have that high sampled reconstruction. So in our study, though we trained in a 24 milligray, so that meant the model, that what was going into the model was reconstructed from 800 projections. Ultimately in testing, we were interested in if you used 4,800 projections for your 4 milligray image. So it's two different acquisitions on what we trained and what we evaluated on.
Good, thank you.
Thanks.
Okay, any other questions? If not, we can probably conclude. And thank you, everyone who participated, and we'll meet next time. And I'm sure Magdalene will send us an announcement about the next seminar.
Okay, thank you.
Thank you.
Take care.